Provide the missing products and reaction conditions for the reactions below. Be wary of arrow directions. All right, which means are you going from which structure to which structure? All right, so here we have a nitrile with a phenyl attached. Okay, we're treating this with a Grignard reagent. Grignard reagents can attack a nitrile at carbon. Right, it's going to push electrons up to nitrogen, and it's going to sit there until we protonate it with HCl, and in the presence of water, that forms an imine. It forms an imine from the acid, but in the presence of water, an imine is hydrolyzed to a carbonyl. Okay, so you're going to form a phenyl ethyl ketone under aqueous HCl conditions. Right? Ketones can be reduced by sodium borohydride. That gives you a secondary alkoxide, and acetic acid protonates the secondary alkoxide, and so we end up with our phenyl ring that's attached to our former nitrile carbon. This has an OH on it from the reduced carbonyl. It has an ethyl group on it from the Grignard reagent attacking in the first step, and it has a hydrogen that came from sodium borohydride. Right? So we're generating a secondary alcohol in this case. All right. Now, if we treat a nitrile with aqueous acid conditions, HCl, water, and heat, so just delta. I know it's a triangle, but it's also a Greek letter. It indicates heat. We can go to an amide. All right. So this is the next one. This arrow is pointing up. All right. So it's asking how do we go from the acid to the amide. All right. So the best way to do this is to first treat with thionyl chloride, SOCl2. That gives you an acid chloride, which of course is our most electrophilic carbonyl species, and so we just treat this with 2 equivalents of ammonia, 1 to attack the acid chloride and 1 to deprotonate the resulting positively charged nitrogen to give us our amide product. All right, the next one, this is reduction selectivity. So let's focus on the arrow. Again, we're moving from right to left here. Be careful to watch that on the exam. All right, so here we have a situation where we have an ester here and we have an aldehyde here. All right, you should all be comfortable with, at least by the time you take the exam, esters are significantly less reactive than aldehydes. All right, so in this case, the more reactive substrate is being reduced. Right, our aldehyde is being reduced and our ester is not. All right, and so you have to ask yourself, do I know of anything that can reduce an aldehyde but can't reduce an ester? And the answer is sodium borohydride can do that. And since we have a hydrogen on our oxygen, it means that we've protonated the alkoxide that would be generated by the borohydride. So we did have to protonate that with something. Okay, H plus is fine. If you want to just say HCl or some other acid, that's fine. You'll notice here in the next question, I've just written H3O plus X minus. Okay, so LaH, lithium aluminum hydride. Note we're going from left to right. All right, so we're treating the same substrate with now a specified reagent, LaH, and in excess, which means there's a whole ton of it. All right, so whatever it can do, it will do. And so LaH will reduce an ester all the way to an alcohol, and if it can reduce an ester, you can be sure it can reduce an aldehyde. And so that would give us 2 primary alkoxides, but we do have the acid condition to follow up with, the H3O plus. And so we're going to end up with a symmetric diol on our phenyl ring. All right, The next problem is much more involved. Okay, the next problem, here we have, again, noting where the arrow, we're going from left to right. So we have an ester that's not changing. We have a ketone that is changing. And we have an aldehyde that's not changing. Okay? Now, this should seem strange because you should be comfortable with the fact that aldehydes are more reactive than ketones. And so we do not know of any reagent that can selectively reduce a ketone over an aldehyde. Okay? And so this is a case where we have to protect the aldehyde. So we use the fact that the aldehyde is more reactive. All right, so we're going to treat this with, say, methanol and acid. All right, this puts on an acetal, or it converts the aldehyde carbon to an acetal. Acetals are completely stable to basic conditions, which is what hydride reagents are. Right? Hydride, negatively charged, it's basic, right? So once we have the aldehyde in acetal form, it can't be reduced. And so now we have a ketone left and we have an ester left. And we know a reagent that can reduce a ketone but can't reduce an ester. And again, that is sodium borohydride. NaBH4. All right, that gives us a secondary alkoxide. And then we can treat this with H3O+. So note that I used H+ here. I didn't use H3O+ here because we don't want water interfering with methanol converting the carbonyl to the acetal. All right, but here we use H3O+ because not only do we want to protonate the reduction alkoxide so we get our alcohol, but we also want to get the aldehyde in our final product. And using aqueous acid conditions, we can convert that acetal back to the aldehyde. All right, so this is a more complex synthesis question, but it's nothing you guys haven't seen before.